Scientists finally found where almost every meteorite comes from. On the night of February the 15th, 2013, a streak of light tore across the sky over Chelyabinsk, Russia. Fragments of that object rained down over the Ural region, and within days scientists were holding pieces of it in their hands. They could weigh it, cut it, study its crystal structure under a microscope. What they could not tell you with any real confidence was where it had come from. Not the general neighborhood. Everyone agreed it had arrived from the asteroid belt somewhere between Mars and Jupiter. What they couldn't say was which asteroid, which family, which collision, in which epoch. That gap in knowledge is strange when you sit with it. We have driven wheeled laboratories across the surface of Mars. We have flown a spacecraft through the tail of a comet and brought grains of it home in a sealed capsule. We have a probe sitting right now on approach trajectories built from decades of orbital mechanics, so precise that engineers can promise a landing within meters. Think about what that means for a discipline. Geologists on Earth can pick up almost any stone and, with enough patience, trace it to a formation, a mountain range. Meteoriticists, by contrast, have spent the better part of 2 centuries handling objects that arrive with no context at all, no strata beneath them. It is a little like being handed a letter with no postmark, no return address, and no signature, and being asked to say with confidence which house on which street it was mailed from. Scientists got remarkably good at reading the letter itself, its chemistry, its age, its mineral structure. What they couldn't do, for the overwhelming majority of cases, was identify the house. Every rock that lands carries its own small, sealed archive. Chemists can measure the ratios of oxygen isotopes trapped inside it and tell you, broadly, what kind of body it broke off from. They can measure how long cosmic rays have been striking its surface, a kind of radiation clock that starts ticking the instant a fragment is exposed to open space. And still, for the vast majority of the specimens sitting in drawers in museums from Chicago to Vienna to Tokyo, this is the story of how that changed. Not gradually, not through some slow accumulation of guesswork, but in the span of about 5 weeks in the autumn of 2024. They didn't just add one more meteorite to the small pile of ones we understood. They took the entire known catalog, more than 70,000 specimens collected and cataloged over centuries. Not to a broad category, not to somewhere in the belt. To 3 specific families of asteroids, each one born from a specific collision, at a specific and now known moment in the deep past. To understand why this took so long, and why solving it required a combination of techniques that had never before been pointed at the problem together. Every year, tons of extraterrestrial material rain down onto the Earth. The vast majority of it is dust, tiny grains too small to survive entry or too small to ever be found once they land, scattered across oceans and ice sheets and forests where no one will ever pick them up. But some fraction of that material survives as chunks large enough to punch through the atmosphere, burn brilliantly, and land as an object you could hold in your hand, or in rare cases, an object large enough to level a forest, as one did over the Tunguska River Basin in 1908, flattening some 2,000 square kilometers of Siberian taiga in an instant, without leaving so much as a definitive crater behind. Of that survivable material, scientists have formally classified and cataloged more than 70,000 individual meteorites. They sit in museum collections and university vaults around the world, cut into slices, polished, analyzed down to their isotopic ratios. We know an enormous amount about what they are made of. Iron-nickel alloys forged in the cores of shattered planetesimals. Stony chondrites containing chondrules, tiny spherical droplets of once molten rock that formed in the earliest years of the solar system and have barely changed since. Carbon-rich chondrites carrying organic compounds and traces of water, chemical fossils from the birth of everything. Some of these specimens have been sitting in drawers for 100 years or more, cataloged by scientists who never imagined a computer, let alone one capable of simulating 1,000,000 years of orbital drift in an afternoon. Walk through the storage vaults of any major natural history museum, and you will find rows and rows of these fragments, each one labeled with a date and a place of discovery. A field in Kansas, a riverbed in Chile, a stretch of Antarctic blue ice where dark stones stand out starkly against the white, and almost nothing beyond that. A fine date and a fine location, and then a blank space where the true history of the object ought to be. But composition is not origin. Knowing what a rock is made of tells you about the kind of body it broke off from, whether that parent was rocky or metallic, wet or dry, primitive or differentiated. It does not tell you which asteroid. It does not tell you when the collision happened that knocked it free, or what that collision looked like, or what else came from the same event. Before this new research, scientists had only managed to trace about 6% of all known meteorites to a specific parent body. And even that 6% leaned almost entirely on 3 sources we happen to have independent confirmation for: the Moon, Mars, and the asteroid Vesta, all 3 of which we have visited with spacecraft, in the case of the Moon and Mars, walked on or driven across. Lunar meteorites match lunar rock samples returned by astronaut missions. Martian meteorites carry trapped gas that matches, almost exactly, the atmosphere measured by landers on the Martian surface. Vesta's fingerprint was confirmed once the Dawn spacecraft orbited it directly and gave scientists a mineralogical signature to check meteorites against. For everything else, for the ordinary chondrites that make up the overwhelming bulk of what falls to Earth, there was no equivalent smoking gun. No spacecraft has landed on the specific asteroid responsible for the rock in your local museum's display case. In nearly all cases, so scientists were left working backward from fragments with no clear thread connecting them to a source. 94% of the catalog, in other words, sat in a kind of scientific limbo, perfectly well understood as objects and almost entirely mysterious as travelers. An entire scientific discipline, built up over 2 centuries of careful, patient work, had gotten extraordinarily good at describing what its subjects were, while remaining almost entirely silent on where they were from. This is where the new research begins, and it begins not with meteorites at all, but with asteroid families. An asteroid family is the debris field left behind after 2 bodies in the main asteroid belt collide. Picture the belt itself first, a broad donut-shaped region of space between the orbits of Mars and Jupiter, populated by more than 1,000,000 bodies larger than a kilometer across, and countless smaller fragments, all orbiting the Sun in roughly the same plane, all moving at different velocities on slightly different paths. Collisions in this environment are not rare, cosmically speaking. Over billions of years, larger asteroids get struck by smaller ones at velocities of several kilometers per second, fast enough to shatter rock and scatter fragments across a wide range of new orbits. When a large asteroid, one measuring more than 30 kilometers across, is broken apart in such a collision, it doesn't just produce 2 pieces. It produces thousands, sometimes hundreds of thousands, of fragments ranging from boulders to fine gravel, all sharing similar orbital characteristics because they all inherited their velocity from the same shattered parent. Over time, these fragments spread out along the original orbit, but they remain identifiable as a cluster, a family, distinguishable by their shared orbital elements: semi-major axis, eccentricity, inclination. Astronomers have cataloged dozens of these families across the belt, some ancient and diffuse, others tight and clearly recent. Seen from above, The belt would look less like a uniform ring of gravel and more like a crime scene photograph from orbit. Clusters and streaks and clumps, each one the fading evidence of some ancient impact, layered over each other like generations of chalk outlines. Some of those outlines are crisp and recent, still holding their shape. Others have blurred almost to nothing, smeared across the orbit by hundreds of millions of years of gravitational nudging, until only a statistical trace remains, visible to careful analysis but invisible to the eye. 3 of these families sit at the center of the 2024 discovery. They are called Charon, Coronis, and Massalia, and each one represents a specific, catastrophic breakup event whose age scientists can now pin down with real precision. The Charon family is the youngest and, in some ways, the most elegant case because its age is unusually well constrained. It formed when a larger asteroid was struck and shattered roughly 5.8 million years ago. That might sound like an enormous span of time by human standards, but in the context of the solar system's 4.6 billion year history, 5.8 million years is essentially yesterday. Because the collision happened so recently, the resulting debris field hasn't had time to spread out and blend into the general background noise of the belt. Its members still cluster tightly in orbital space, tight enough that astronomers can trace their orbits backward with software and watch them converge, almost like watching a video of an explosion run in reverse, until they collapse back into a single point of origin. There is something almost eerie about that reversal. Thousands of fragments scattered across millions of kilometers today, all sliding backward through simulated time until, at one precise instant, they occupy the same point in space, the ghost of a single vanished asteroid. Run the simulation forward again, and you watch that single point bloom outward into the scattered cloud we observe today, the entire 5.8 million year history compressed into a few seconds on a screen, an asteroid dying, and its wreckage drifting apart in real time. The Coronis family is older and more complicated because it isn't really one event but a layered history of several. Within the broader Coronis family sits a younger subcluster, sometimes called Coronis II, believed to have formed somewhere between 10 and 15 million years ago and buried deeper still, an even older subcluster, Coronis III, dated to roughly 83 million years ago. Think of Coronis less as a single collision and more as a family tree, generation after generation of breakups happening within roughly the same orbital neighborhood, each one adding its own layer of fresh debris to a region that was already full of older fragments. It is a demolition site built on top of an older demolition site, itself built on top of one older still, each layer of rubble slightly harder to distinguish from the layer beneath it. Untangling that layered history required sorting fragments not just by their present-day orbits, but by the subtle differences in how far the Yarkovsky effect had already carried each one, a way of reading, in the scatter of the debris, roughly how long each subcluster had been aging. And then there is Massalia, the oldest, and as it turns out, the single most important source in the entire study. The team's best estimate places the Massalia breakup at approximately 40 million years ago, though because the debris field is older and more dispersed, that age carries more uncertainty than the tightly clustered Charon family. Massalia's parent body was large, and its breakup was violent enough to send an enormous quantity of fragments into orbits that, over tens of millions of years, would slowly evolve toward Earth-crossing paths. 40 million years ago, for scale, is roughly the same span of time separating us from the last days when whales still had legs and walked, however awkwardly, on land. The debris from that one collision has been drifting, breaking, and falling ever since, a single afternoon of violence in the belt whose consequences are still, quite literally, raining down on us. Identifying that these 3 families existed, and roughly when they formed, was already known science before 2024. Asteroid families have been cataloged for decades using ground-based and space telescope surveys. What the new work did was something far more ambitious. It built a bridge, a genuinely rigorous quantitative bridge between these asteroid families in the belt and the specific meteorites that scientists have been picking up off the ground here on Earth for centuries. That bridge was built out of 3 separate lines of evidence, each one independently pointing toward the same conclusion, which is precisely why the result has been received with so little skepticism. Independent convergence is the strongest kind of proof available to observational science, when you cannot run the experiment again in a lab. The first line of evidence came from dynamical modeling. Essentially, orbital physics run forward and backward across millions of years. Once you know a family's approximate age and its members' current orbits, you can simulate how small fragments would have drifted away from that original cluster over time, nudged by a subtle but crucial effect called the Yarkovsky effect. This is a small but persistent thermal force. An asteroid absorbs sunlight on its day side, heats up, and re-radiates that heat later, after its rotation has carried the hot spot toward the night side. That re-radiated heat provides a tiny, continuous thrust that slowly, over millions of years, shifts an object's orbit. It sounds too small to matter, an effect that pushes on a body with less force than a sheet of paper, but with enough time, tiny forces compound. Over a few million years, the Yarkovsky effect is exactly what can nudge a fragment out of the main belt and onto a path that eventually crosses Earth's orbit. The effect depends crucially on size. Smaller rocks, with less mass to move and more surface relative to their volume, feel the push far more strongly than large boulders do, which is precisely why it is the meter-scale fragments, the ones capable of surviving a fiery drop through the atmosphere and landing as a meteorite, that get shepherded most efficiently toward Earth-crossing orbits, while the largest chunks of shattered parent body tend to stay close to where they started. Researchers modeled this drift for huge numbers of simulated fragments from each of the 3 families and asked a simple question. Given enough time, what fraction of them end up on trajectories that intersect Earth? The answer for Charon, Carinus, and Massalia was an enormous fraction, far larger than you'd expect from older or more distant families. Running these simulations at the scale required millions of individual test particles, each tracked across tens of millions of simulated years, was itself only practical because of the computing power that had become available in the years leading up to this research. A calculation like this, attempted decades earlier, would have taken longer than the careers of the people running it. The second line of evidence came from spectroscopy, observing the actual light reflected off asteroids within these families using large ground-based telescopes, including instruments operated by the European Southern Observatory in Chile. Different minerals reflect and absorb sunlight at different wavelengths, producing a spectral signature almost like a fingerprint. Researchers took spectra of asteroids within the Massalia family and compared them directly against the spectral signatures of chondrite meteorites, the most common type of stony meteorite recovered on Earth. The match was strong, not a vague resemblance, but a specific, mineralogically consistent match between the light reflected off asteroids currently sitting in the Massalia family and the light reflected off polished slices of meteorites sitting in laboratory collections. To get that match, researchers had to point some of the largest optical telescopes on Earth at objects that are individually faint and small and utterly unremarkable to look at, dim points of reflected sunlight, hundreds of millions of kilometers away, distinguishable from the background stars only by their slow crawl across the sky night after night. Each observation might yield only a faint, noisy curve of light split into its component wavelengths, and it took patient, repeated measurement, asteroid after asteroid within the family, before the pattern became undeniable. This cluster of debris and this common class of meteorite share a chemical signature too specific to be coincidence. The third line of evidence, and in some ways the most viscerally convincing, came from fireball networks, arrays of cameras, some operated by government agencies, others run through citizen science and university partnerships, positioned across continents specifically to catch meteors in the act of falling. When a meteor is captured by two or more cameras at different locations, triangulation lets researchers calculate not just where it landed, but the trajectory it followed on the way in, and from that trajectory, its orbit before it ever encountered Earth's atmosphere. This is, in effect, catching a meteorite falling and reading its return address off the envelope before it hits the ground. For a growing number of recovered meteorites, scientists now have not just the composition of the rock, but the precise orbit it was on in the moments before impact, and that orbit can be checked directly against the orbits of the three asteroid families. It is worth picturing what that actually looks like on the ground. A farmer somewhere hears a boom, finds an odd dark stone in a furrow the next morning, and reports it. And because a camera 200 kilometers away happened to catch the same fireball crossing the sky the night before, that unremarkable stone arrives at the laboratory not as an anonymous rock, but as an object with a documented flight path stretching back into the asteroid belt. Multiply that single case by dozens of similar recoveries, spread across different networks and different continents, and you start to see why this third method carries so much weight. It doesn't rely on modeling or inference at all. It is a direct, photographed measurement of a rock's motion through space in the final seconds before it became a specimen in someone's collection. 3 separate methods, using 3 different kinds of data, all converging on the same answer. And the answer is startling in its scale. Massalia, Karen, and Carinus together account for approximately 70% of all known meteorite falls on Earth. Not 70% of some narrow category. 70% of the entire catalog. More than 70,000 specimens spanning centuries of collection. Most of that debris tracing back to just 3 collisions, 3 specific moments of violence in the asteroid belt, spread across a window of time from just under 6 million years ago to around 40 million years ago. Massalia alone accounts for roughly 37% of all known meteorites, making it by a wide margin the single largest identified source of extraterrestrial material recovered on this planet. One collision in the main asteroid belt, tens of millions of years ago, is responsible for more than a third of everything we have ever picked up. Stop and consider that for a moment. Somewhere in a museum drawer, in roughly 1 out of every 3 meteorite specimens on Earth, sit a fragment of the exact same shattered parent body, scattered across different countries, different collections, different centuries of discovery, and until recently no one studying any single one of those fragments could have told you it shared an origin with all the others. A meteorite cataloged in a Vienna museum in the 1800s and a meteorite recovered from an Australian desert last year might, in this light, turn out to be siblings, torn from the same body in the same violent instant, 40 million years before either one was ever found. When you add in the meteorites that were already traced through other means, the Moon, Mars, Vesta, plus a handful of additional smaller families identified through the same research, the total picture becomes even more complete. With this study, the origin of more than 90% of all known meteorites has now been identified. A field of study that, for as long as it has existed, has had to shrug at the question of where did this come from for the vast majority of its specimens can now answer that question for nearly all of them. It's worth sitting with how strange this actually is historically. Meteorites have been recognized as objects falling from the sky since at least the 18th century, when a shower of stones near L'Aigle, France, in 1803 convinced even skeptical academies of science that rocks really do fall from space, rather than being kicked up by terrestrial volcanoes or lightning strikes, as some had proposed. Before that event, it was entirely respectable for a scientist to insist that stones simply could not fall from an empty sky, and museum curators occasionally threw out meteorite specimens because a rock supposedly from the heavens seemed less credible than a rock that had merely been misfiled. Since Legel, generations of scientists have collected, classified, and studied these objects with increasing sophistication, building an entire discipline around materials that, until 2024, mostly arrived without a return address. 2 centuries of painstaking classification, of building ever more precise systems for sorting chondrites from achondrites, irons from stony irons, and at the end of all that careful sorting, the field still could not answer the single question every visitor to a meteorite display inevitably asks. But where did it actually come from? Sarah Russell, a planetary scientist at the Natural History Museum in London who was not part of the research team, described the moment in a phrase that captures the field's reaction well. She called it a major breakthrough for meteor scientists, comparing the discovery to finding a pot of gold at the end of a rainbow. For a discipline that has spent centuries analyzing objects whose origin was essentially unknowable, that's not an exaggeration. It's a fair description of what it feels like to suddenly be handed the answer. But the story doesn't stop at identifying the 3 families. One of the most remarkable threads running through this research reaches back not just tens of millions of years, but hundreds of millions into a period of Earth's history long before anything resembling a mammal or a flowering plant or really anything we'd recognize walked or grew on this planet. Around 466 million years ago, during what geologists call the Middle Ordovician period, something happened to Earth's rate of meteorite infall that left a very specific, very durable signature in the rock record. Scientists studying limestone layers from this period, particularly in Sweden, have found an unusual abundance of fossil micrometeorites embedded directly in the sediment, tiny grains of extraterrestrial rock that settled to the seafloor and were locked in a stone as the layers formed. These aren't rare, exotic finds either. Quarry workers cutting limestone for flooring and countertops have, for decades, been unknowingly slicing through rock containing hundreds of fossilized specks of space debris, grains that fell into an ancient sea and were entombed there for nearly 500 million years before anyone thought to look for them under a microscope. It is a strange thought on its own. Somewhere right now, a kitchen countertop or a hallway floor, quarried from that same limestone, may be carrying inside it a grain of rock older than the dinosaurs, older than the first fish that crawled toward land, sitting there quietly under a bowl of fruit. Alongside these micrometeorites, the geological record from roughly the same window shows an unusually high number of impact craters dated to the same era, scattered across what is now Sweden and elsewhere. Together, these lines of evidence point to a sustained, elevated period of meteorite bombardment, a kind of extended shower of debris raining onto the planet over an extended stretch of geological time, rather than a single catastrophic strike. The material recovered from this ancient shower has a specific chemical identity. It is L-chondrite material, the same broad class of ordinary chondrite that makes up the most common type of meteorite falling today. And this Middle Ordovician bombardment coincides, suspiciously closely, with major shifts recorded elsewhere in the geological and fossil record from the same era. Evidence some researchers connect to a cooling climate and a significant reorganization of marine biodiversity as ecosystems adjusted to a changing world. The causal chain between an asteroid breakup, a sustained increase in meteoritic dust and debris entering the atmosphere, and a shift in Earth's climate and ecology is not simple. and scientists studying it are careful about overstating the connection. But the timing is difficult to ignore, and it has been a subject of serious scientific interest for years. Something in the asteroid belt broke apart around 466 million years ago, sent a huge quantity of material toward Earth, and that arrival lines up with one of the more curious turning points in early animal evolution. Until 2024, that ancient breakup was essentially an orphan event. Scientists could see its fingerprints in the sedimentary record. They could identify the chemical signature of the material as chondrite. They could even estimate roughly when it happened, but they had no confirmed candidate for which asteroid or which collision in the belt had produced it. The new research changes that. The same investigation that identified Massalia as the source of 37% of today's meteorite falls also makes Massalia the leading candidate for the parent body responsible for that Ordovician bombardment nearly 500 million years ago. If that identification holds, it means a single collision event created a source of material so productive that it has been raining down on this planet in some form for tens of millions of years, seeding an ancient sea floor with grains of nickel and iron 466 million years ago, and still today occasionally streaking across a modern sky and landing in someone's driveway. The same asteroidal debris field, doing the same job, across a span of time, so large it brackets almost the entire history of complex life on land. It's a genuinely strange thing to consider, that a shower of extraterrestrial gravel that may have nudged Earth's climate and its oceanic ecosystems during the Ordovician, and the rock that might land in a field in Kansas next year, could trace back to the exact same asteroid, shattered in the exact same instant, 400 million years before either event took place. Trilobites crawling across a shallow Ordovician seafloor, and a farmer in the American Midwest checking his fields after a strange light in the sky, separated by nearly 500 million years, and every extinction and evolutionary explosion in between, connected by nothing more than the leftover gravel of one violent afternoon in the asteroid belt. Now, having laid out how large and how old this source turns out to be, it's worth turning to the part of the story that gives the whole discovery its edge, the part that keeps this from being a simple, tidy resolution. Because the very features that make Charon, Caronis, and Massalia such prolific sources of meteorites today are the same features that guarantee they will not remain the dominant sources forever. Here is the mechanism laid out plainly. When a large asteroid breaks apart, the debris field it produces is, at first, extraordinarily rich in small fragments, boulders, gravel, and dust, along with a smaller number of larger chunks. It is specifically the small fragments on the order of meters to tens of meters across that are most efficiently pushed by the Yarkovsky effect toward Earth-crossing orbits. And it is exactly those small fragments that survive atmospheric entry as meteorites we can collect. A fresh asteroid family, in other words, is a kind of reservoir stocked at the moment of its creation with an enormous supply of exactly the right size of material to eventually become meteorites falling on Earth. But that reservoir does not refill itself. As millions of years pass, those small fragments are gradually ground down, further shattered by subsequent smaller collisions within the family, or slowly drift away entirely once the Yarkovsky effect has finished nudging them out onto Earth-crossing paths, or simply get consumed, falling to Earth or into the Sun, or being ejected from the solar system altogether. The supply is finite. It was set the moment the parent asteroid shattered, and every million years that passes afterward depletes it a little further. Given tens of millions of years, an asteroid family transitions from being a rich, productive source of meteorite material into what researchers describe as a depleted family, one whose reservoir of small, Earth-crossing ready fragments has been steadily eroded away by its own ongoing collisional history. It is not unlike a gravel quarry that was stocked once, catastrophically, in a single blast, and has been drawn down ever since, load by load, with no new blast to refill it. Eventually, the quarry empties out, and no matter how carefully anyone searches it, there simply isn't fresh material left to find. This is precisely why Charon, Caronis, and Massalia dominate the picture today. They are, relatively speaking, young. Charon, at just under 6 million years old, is barely depleted at all, its debris field still tightly clustered, still rich with fresh material. Caronis, layered across multiple breakup events spanning roughly 10 to 83 million years, is further along in the depletion process but still productive. And Massalia, the oldest of the three at around 40 million years, still supplies more meteorite material than any other single source, but is, relatively speaking, further down that same road toward eventual depletion than Charon is. Older asteroid families, ones that broke apart hundreds of millions or billions of years ago, contribute comparatively little to the meteorite record today, not because those ancient collisions produced less debris originally, but because they've simply had far more time to exhaust their supply of small fragments. Their reservoirs ran dry long ago. The debris that remains from those ancient breakups still exists, still orbits, but it has evolved into distributions of asteroids that no longer efficiently shed material bound for Earth in useful quantities. Somewhere in the belt right now, there are almost certainly families of exactly this kind. The burned-out remnants of collisions from a billion years ago, still faintly traceable to a careful eye with a telescope, but contributing essentially nothing to what lands on Earth this century. They're the ghost towns of the asteroid belt, still standing, still mapped, but long emptied of anything worth taking. This gives the whole picture a strange, almost ecological quality. Asteroid families aren't fixed, permanent sources of meteorites, the way a spring might be a permanent source of water. They behave more like something with a lifespan, born violently in a single catastrophic collision, productive and rich for tens of millions of years afterward, and then gradually exhausted, fading into the background as their easily accessible material is used up. Charon, Caronis, and Massalia happen to be caught, right now, in the productive middle of that lifespan, which is precisely why they dominate the current meteorite record so overwhelmingly. Given enough time, tens of millions of years from now, their contribution will fade, and whatever collision or collisions happen next in the asteroid belt, breakups that may not have occurred yet, will take their place as the next dominant source of material raining down on Earth. That reframing matters because it changes the character of what was actually discovered. This isn't a map of the asteroid belt that will remain accurate forever, a fixed answer to a fixed question. It's a snapshot of a dynamic, ongoing process, a photograph of a system that is constantly producing new debris, constantly depleting old debris, and constantly shifting which families happen to be feeding material toward Earth at any given geological moment. The three families dominating today's meteorite falls are, in a real sense, simply the most recent chapter in a story that has been running since the asteroid belt first formed, and will keep running as long as collisions continue to happen out there among the leftover rubble of planet formation. Somewhere out there, right now, two bodies may already be on a slow, silent collision course, the next Charon or Massalia, still years or centuries from its moment of impact, quietly setting up the next reservoir that some future scientist or some future civilization will eventually have to trace. It's also worth being honest about what remains unresolved, because the story didn't end with the 2024 papers, and treating it as a fully closed case would overstate things. A follow-up study published in the spring of 2025 drawing on data from global fireball camera networks combined with a technique called cosmic ray exposure dating, which measures how long a rock's surface has been exposed to space radiation before it landed, went back through a set of individually tracked meteorite falls and matched them, one by one, against the specific subclusters within these families. Of 12 meteorites examined in that follow-up work, 3 were traced specifically to the Charon cluster, consistent with that family's age of about 5.8 million years. 2 were matched to the Caronis II subcluster, with its estimated age of 10 to 15 million years. And at least one meteorite appears to carry an exposure age consistent with the much older Caronis III subcluster, dated to around 83 million years, adding real, physical, sample-based confirmation to a subfamily that had, up to that point, only been identified through orbital modeling. 12 rocks, individually recovered on different continents at different times, and each one, once its exposure history was read carefully enough, turned out to be carrying a kind of internal clock, ticking away since the moment it was blasted free of its parent body. It is a small study. Numerically, 12 specimens is not a large sample by the standards of most sciences, but each one of those 12 had to be independently photographed falling, independently recovered from the ground, and independently measured in a laboratory before it could be checked against the orbital story, which makes even a small number like that feel earned rather than assumed. That same 2025 review also turned up something the original headline results didn't fully capture: additional smaller source families beyond the 3 headline names. A cluster of H. chondrite meteorites, for instance, appears to trace back not to Charon, Caronis, or Massalia at all, but to a separate, less prominent asteroid family called Nele. It's a reminder that 3 families explain 70%, and more than 90% is now explained overall, is an extraordinary result, genuinely one of the most significant in the history of meteorite science. But it is not the same as saying every last meteorite in every collection now has a confirmed, unambiguous parent. The remaining fraction, the meteorites that don't fit neatly into Charon, Caronis, Massalia, or the handful of already known sources like the Moon, Mars, and Vesta, are still being worked through, family by family, cluster by cluster, as researchers apply the same 3-pronged method: dynamical modeling, spectroscopy, and fireball trajectory reconstruction, to the harder remaining cases. If the pattern holds, it is likely only a matter of time, probably not decades this time, but years before Nele and families like it get their own version of this same treatment, and the 90% figure creeps still closer to 100. There's also the small matter of the 7.6 versus 7.5 million year figure for the Caronis breakup age, a tiny discrepancy that's worth mentioning briefly, not because it matters scientifically, but because it says something about how science actually moves from research paper to public understanding. The original peer-reviewed paper gives the age of that particular breakup as approximately 7.6 million years. Almost every press release and news summary that followed rounded that figure down to 7.5. It's a trivial rounding difference, almost certainly just simplification for a general audience rather than any real disagreement among scientists, but it's a useful reminder that even a landmark discovery like this one passes through several hands, several summaries, several simplifications before it reaches the public. And small numbers can drift a little in the retelling, even when the underlying science is completely solid. None of that undercuts the central achievement here. It's worth returning, at the end, to just how large a gap this research closed and how quickly it closed it. For roughly 2 centuries, since scientists first accepted that rocks really do fall from the sky, the overwhelming majority of meteorites in every collection on Earth carried no confirmed origin beyond somewhere in the asteroid belt. 6% traced, 94% essentially anonymous. Then, across a span of about 5 weeks in the autumn of 2024, that number flipped and more than 90% of everything we've ever picked up now has a name, an age, and a location attached to it. Charon, Caronis, Massalia. 3 collisions in 3 different corners of the main asteroid belt at 3 different moments over the last 40 million years, each one shattering a body larger than 30 kilometers across and scattering its remains across the inner solar system. And buried inside that story is a genuinely strange piece of continuity. A rock that fell in the Ordovician period for 166 million years ago, when the most complex life on Earth lived entirely in the ocean, and a rock that might land in someone's garden next spring may well have come from the exact same shattered parent body, separated not by geography, but by an almost incomprehensible span of time. Both of them fragments of a single act of destruction in the asteroid belt, still playing out one piece at a time across hundreds of millions of years. The asteroid belt has never stopped colliding with itself. It won't stop now. Charon, Caronis, and Massalia are, in the long view, simply the most recent violence in a process as old as the solar system. And one day, tens of millions of years from now, their debris will thin out, their reservoirs will run dry, and some new collision, one that may not have happened yet, will take their place as the source of most of what falls from the sky. For now, though, for the first time since anyone started picking meteorites up off the ground and asking where they came from, we finally know the answer for almost all of them. 3 collisions. 3 families. 90% of everything that has ever fallen traced at last back home. Brighter for a few seconds than the sun. It detonated some 30 kilometers up, and the shock wave blew out windows across 6 cities, injuring over 1,000 people who had done nothing more than stand near glass. Had first knocked this rock loose from its parent body and sent it on a multi-million-year drift toward a Tuesday morning over Siberia, years in advance. And yet, for the ordinary rock that occasionally falls out of the sky and lands in someone's backyard or a farmer's field, we have historically had almost nothing to say about its origin except, somewhere out there, a specific bed of sediment laid down in a specific era. No neighboring outcrop to compare against. Nothing but the rock itself and the brief violence of its entry. And use that to estimate roughly how long it drifted before it fell. They can slice it thin enough to shine light through it and read the mineral grains like a fingerprint. All of that careful analysis stopped at the edge of the same wall. This rock is a chondrite. This rock is roughly this old. This rock cooled at roughly this rate. And then silence where the address should have been. When a group of researchers working across France, Chile, and the Czech Republic published a set of papers that did something remarkable and traced the overwhelming majority of them back to their source. You have to understand what a meteorite actually is and how strange the numbers around it are.